Welcome students. Today we are going to see about precipitation titration. First definition. It is a special type of titrimetric procedure. Involves the formation of precipitates during the course of titration. The titrant reacts with an analyte forming an insoluble material and the titration continues till very last amount of analyte is consumed. So, in precipitation titration, chemical reactions result in the formation of a precipitate. In this type of titration, standard solution and the reactant substance react and lead to slightly soluble salts as a primary reaction product or precipitate. In precipitation titration, precipitating agents are used to determine many analytes. Examples: silver nitrate is used as a precipitation agent for the determination of chloride. Next, it involves two types, direct method and indirect method. First, what is an precipitate? The formation of solid inside another solid or solution during chemical reaction or by diffusion on the solid is known as precipitation. The solid form is said to be a precipitate if the reactions occurred in liquid, whereas it is said to be a pellet. Supernatant is a liquid that remains above the precipitate or the pellet. Purity of precipitate. After the chemical reactions, the precipitate formed in the solution is not as pure as liquid. So, the precipitate must be pured. A precipitate contained with the substance present in the mother liquor is said to be co-precipitate, and the process of this contamination is known as co-precipitation. So, the contaminated substance present in the mother liquor is called as co-precipitate, and the contamination process is known as co-precipitation. This process involves the absorption of foreign substance and the surface of the particle in the solution and occlusion of observed foreign substances during the crystallization from primary particles. Minimum absorption occurs in the microcrystalline precipitates. Example: silver iodide precipitates on silver acetate and barium sulfate on alkali nitrates, while maximum occurs for gelatinous precipitates. Many errors can be also introduced during the titration by the process of post-precipitation, in which precipitation takes place after the formation of the first precipitate on the surface. This results with sparingly soluble substances that formed supersaturated solutions generally, and common ion effect with the primary precipitate is involved. Example: precipitation of calcium oxide in the presence of magnesium, which separates out in the magnesium oxide and the surface of calcium oxide. The longer the time take to conduct, the greater precipitation occur in the surface of the first precipitate. Then reactions must satisfy this condition. So, what and all conditions the precipitate must satisfy in a reaction? Precipitate must be partially insoluble. They should not be fully dissolved in the solution. They must be rapid. The precipitation should be very rapid. Possible to detect equivalent points, and the precipitate is used to detect the equivalent point. Methods based on precipitation of insoluble silver is known as argentiometry. So, precipitation of insoluble silver is known as argentiometry. Halogens can be detected by the precipitation as sparingly soluble mercury salts, mercury chloride, and mercuric iodide is called mercurometric. Next is some of the problems during precipitation. The main problem during the formation of precipitate is colloidal dispersion of finely divided solid may undergo flocculation and coagulation. This allows them to deposit such a cake on the filter paper when being filtered. When the precipitate on the filter paper is washed, it fails to undergo reprecipitation. Substance with particles 0.1 micrometer to 1 nanometer forms the particle of colloidal dispersion. Particles with 10 the power minus 2 micrometer or 10 micrometer in diameter are retained in the ordinary quantity to filter paper. Therefore, the colloidal particles of the size 0.1 m or 10 the power minus 8 cm should not be filtered. Due to this property, the colloidal solutions are termed as tube solution. Another difficulty that occurs in gravimetric analysis is supersaturation. It is the process in which concentration of solute is higher than the expected equilibrium solubility under the given conditions of temperature. Then principle. Formation of insoluble product by combination of two ionic species is known as precipitation. The completion reaction is indicated by precipitation of the product. Precipitation reaction is not frequently used in titration because all precipitation reactions do not comply with the desired specification. In water, silver chloride is slightly soluble, having 1.79 into 10 to the power minus 3 gram per liter at 25 degrees Celsius saturation limit. On adding silver nitrate solution to potassium chloride solution, the concentration of silver chloride exceeds the saturation limit, thus resulting in the formation of precipitate. The product of molecule concentration of a ion is constant when the salt is almost insoluble. This product is solubility product of an insoluble salt. So, solubility product. Solubility product is the product of concentration of ions in the saturated solutions of sparingly soluble salts such as silver nitrate is a constant at a given temperature. It can be represented as Ag plus and Cl minus equal to concentration of moles per liter of silver and chloride ions respectively. The polar equilibrium is silver chloride dissociates into silver and chloride where silver positive and chloride negative. The ionic concentration is called equilibrium constant and the end value is solubility constant product, and it has a formula also, n equal to weight by molecular weight. In titrimetric analysis, the requirements for reactions are, we already said, the precipitation reaction should be rapid and quantitative. They should be insoluble. Absorption co-precipitation should not affect the titration. The equivalence point should be detectable and in the during of titration. When ionic product exceeds the solubility product, the solution is supersaturated and precipitation will occur. When ionic product exceeds solubility product, solution is supersaturated. When ionic product is less than the soluble product, solution is not supersaturated or unsaturated and precipitation will not occur. When ionic product is less than the soluble product, is the unsaturated. In quantitative analysis, excess precipitation agent always employed to ensure complete precipitation. So the reaction is barium chloride in the presence of sulfuric acid gives barium sulfate and hydrochloric acid. If less amount of sulfuric acid is employed, ionic product far exceeds the solubility product and there is a complete precipitation. Oxalic acid causes complete precipitation of calcium oxalate from the solution of calcium acetate but not from calcium chloride and calcium nitrate. So calcium acetate reacts in the presence of oxalic acid to give calcium acetate and acetic acid. Acetic acid is a weak acid than oxalic acid, thus it does not suppress the dissociated oxalic acid. The concentration of oxalate ion is sufficient to keep ionic product greater than the solubility product of calcium oxalate. In case of calcium chloride, hydrochloric acid is formed, which is a strong acid and highly dissociated. It suppresses the dissociation of oxalic acid by common ion effect. The oxalate concentration falls below the value recorded to exceed the solubility product of calcium oxalate. The precipitation is therefore incomplete. This explains why calcium oxalate dissolves in HCl but not in oxalic acid. Yes. Next, effect of acid upon solubility of precipitate. Sparingly soluble salts of strong acid, the effect of addition of acid will be similar to that of any other indifferent electrolyte. But if the soluble sparing soluble salt is weak acid, it will give sufficient solvent effect on it. A theory in this reaction, which is chloride ion and silver nitrate are involved in the formation of precipitate. Further, addition of silver nitrate solution will affect the precipitation of silver chloride, which provide the value of equilibrium constants, which exceeds remarkably. Next, effect of temperature upon solubility of precipitate. The solubility of precipitate encountered in the quantitative analysis increase with the rise in temperature is small, but with other is quite appreciable. The solubility of silver chloride is 10 Celsius and 100 Celsius, which is 1.72 milligram and 21.1 milligram respectively. In case of barium sulfate, these temperatures are 2.2 and 3.9 milligram respectively. Wherever possible, it is advantageous to filter while the solution is hot. Rate of filtration is increased. The solubility of foreign substances, thus rendering their removal from the precipitate completes. Effect of solvent upon solubility of precipitate. The solubility of most inorganic compounds is reduced by the addition of organic solvent such as methane, ethanol, propanol, acetone. Addition of 20% of ethanol renders solubility of lead sulfate negligible, thus permitting quantitative separation. Similarly, calcium sulfate separates quantitatively from 50% ethanol. By adding organic solvents, the solubility of most of the organic compounds can be reduced. For example, addition of 20% ethanol by volume permits quantitative separation of lead sulfate precipitate by making its solubility partially negligible. Next, common ion effect. By adding excess amount of ions in slightly soluble salts, its solubility can be reduced. Example, dissociation of slightly soluble salts can be represented by the above condition is equilibrium condition to form the precipitation of salt, and the excess of either ion should be added in the form of another salt. Effect of pH. If the anion of the salt is a conjugate base of weak acid, the solubility of a salt will be increased on decreasing pH. This can be explained with an example. Slightly soluble salt whose anion is conjugate to base of an weak acid. Next, types of precipitation titration. The precipitation titration using silver nitrate with chlorine, bromine, iodines and thiocyanates are mainly used. This precipitation titration is also known as argentometric titration, since silver is always involved during the reaction. Therefore, concluding these titrations have the limited use. As per the endpoint detection method, four main procedures are used depending upon the type of applications. These procedures are followed as Morse method, Wohlhull's method, modified Wohlhull's method, and Fajan's method. First, we have to see about Morse method. This method is named after Carl Friedrich Mohr. In this method, potassium chromate is used as an indicator which produces red-colored silver chromate at the end point when all the chloride ion have reached. So, in 1856, Mohr introduced the Morse method, determination of halide chloride with silver nitrate using potassium chromate solution as an indicator. It is especially used for the determination of chloride. Silver nitrate in the presence of sodium chloride gives silver chloride and sodium nitrate. Precipitated silver chromate, though sparingly soluble in water, is the more soluble than silver chloride, and the red color is due to the silver chromate does not appear until the chloride has been precipitated as silver chloride. The sensitivity of indicator depend upon the concentration, temperature, hydrogen ion concentration of electrode and manner of observing the red colorization. So this method utilizes chromate as an indicator. Chromate forms the precipitate with silver, but this precipitate has a greater solubility than silver chloride. For example, therefore, silver chloride is formed first, and after all, chlorine is consumed. The first drop of silver is in excess will react with the chromate indicator, giving a reddish precipitate. Theory. In Moore's method, the end point is detected when the colored precipitate of chloride or bromide is formed. A neutral solution of chloride ion is titrated with the silver nitrate solution using a small quantity of potassium chromate solution as an indicator. The chromate ion combines with the silver nitrate at the end point, forming a red colored and sparingly soluble silver chromate. Preparation and standardization of silver nitrate. First, 1.2 gram of sodium chloride or 1.6 gram of potassium chloride is dissolved in the water containing 250 ml of volumetric flask, and make up the volume to 50 ml with a conical flask, and 2 ml of 0.1 m potassium chromate indicator is added. The burette is filled with silver nitrate solution and the initial reading is noted. Therefore, the silver nitrate solution is added to the chlorine solution till the red color of the silver chromate appears spread throughout the solution, indicating the end point. Formation of white curty silver chloride lumps also indicates the end point is near. At this point, silver nitrate solution is added dropwise till the yellow colored chromate ions permanently change to red colored silver chromate precipitate. If required, an additional indicator blank is run that then the procedure is repeated in form of two similar titrations in order to obtain a concordant set of readings. Precautions. In this method, neutral medium should be used since in alkaline solution, silver will react with hydrogen ions forming AgOH, so what silver hydroxide. In acidic solution, chromate will converted to dichromate. Therefore, pH of the solution should be kept about 7. There is always some error in this method because dilute chromate solution is used due to the intense color of indicator. This will require additional amount of silver for silver chromate to form. Limitations. Allowable pH range is 6.5 to 10. Below pH 6.5, there is increased in solubility of silver chromate. Above pH 10, the end point comes too late and silver hydroxide is precipitated. If the solution is alkaline, make it acidic with nitric acid, then neutralize it by adding some sodium bicarbonate or borax. If appreciable amount of aluminum salts are present, pH should not exceed 7.2. In reverse titration, iodides and bromates cannot be titrated. Preparations we have already seen. Now we can see applications. Applications of Moore's method. First, chlorides. Chlorides in neutral solution can be determined either by Moore's titration or absorption indicator method by titrating with 0.1 molarity standard solution of silver nitrate. If the solution is acidic, chloride, or calcium carbonate, sodium tetraborate or sodium hydrogen carbonate will affect the neutralization. The neutralization of most of the acid with the ammonia solution followed by addition of excess ammonium ethionate removes the mineral acid. Bromides. Bromides can be determined like chlorides using Moore's titration method. Absorption indicator eosin is the most suitable one, which can be used in dilute solutions and also in presence of 0.1 m nitric acid, but ethanoic acid solutions are preferred. Fluorescence can be used, but faces the same limitations as the chlorides. When using indicator is used, silver bromide flocculates 1% before the end point and red color develops, which is more distinctive, and addition of silver nitrate solution the end point of the precipitate make the magenta color. Next one, Olhardt's method. Olhardt's method is named after Jacob Olhardt's. It is a type of back titration. In 1874, Olhard designed the method of estimation of silver ions in dilute acid solution by titrating against standard thiocyanate solution in the presence of ferric salts, ferric ammonium sulfate as an indicator. It has been extended to estimate chloride, bromide, and another several analyses. Ammonium or potassium thiocyanate solution is used in conjugation with 0.1 m aluminum nitrate in assay of substances which react with nitrate, but that cannot be determined by direct titration with the silver nitrate solution. In this method, to halide solution, a known excess of silver nitrate is treated with 0.1 m ammonia or potassium thiocyanate solution is called Olhardt's method. In this method, precipitate of silver chloride is filtered off and the filter is titrated with the standard sodium thiocyanate solution using ferric ammonium sulfate solution as indicator. At end point, permanent red color is produced due to the formation of ferric thiocyanate. Reactions for Olhardt's method. It is an indirect method of chlorine determinations, whereas excess amount of standard silver is added to chlorine solution containing ferric ions as indicator. The excess silver is titrated with the standard silver cyanate or sodium thiocyanate solution until red color is obtained, which results in the reaction taken with sodium thiocyanate gives ferric ammonium sulfate ions. However, this is affected in several ways. The AgCl precipitate is boiled for few minutes. The precipitate is removed by filtration and then cold filters is back titrated. The Ag particles are prevented from reacting with the thiocyanate by coating with immiscible liquids, example nitrobenzene. The indicator system is very sensitive and usually good results are obtained. The medium should be acidic to avoid the formation of ferric oxide. However, the use of acidic medium together with the sodium thiocyanate titrate increase the solubility of the precipitate, leading to significant error, and this problem has been overcome to maintain procedures. Removal of precipitate of silver chlorides. The reasons for removing the precipitate of silver chloride reacts with the thiocyanate to form change in titer value. In determination of iodide and bromine not need because the reaction is negligible. Next one, modified Olhardt's method. Especially it is used based on the indirect volumetric precipitation titration. In this method, nitric acid solution is used to acidify sodium chloride solution and then presence of nitrobenzene. This solution is treated with the excess amount of standard solution of silver nitrate. Some moles of silver nitrates are also consumed in the reaction with the NaCl, and the remaining unreacted silver nitrate is determined by the titrating with the standard sodium ammonium thiocyanate. In this titration solution, ferric ammonium sulfate, ferric alum is used as an indicator. Nitrobenzene form an organic layer around the precipitate particles of silver chloride, thus rendering it completely insoluble. This prevents silver chloride to react with the ammonium thiocyanate. The nitric acid added prevents ferric ammonium sulfate solution To hydrolyze, formation of permanent brick red color due to the formation of ferric thiocyanate indicates attainment of end point. Sodium reacts with the silver nitrate gives silver chloride plus sodium nitrate plus aluminum nitrate. Preparation. Dissolve 7.6 gram of ammonium thiocyanate in 1000 ml of distilled water. Pipette out 30 ml of silver nitrate into flask. Dilute with 50 ml of water and 2 ml of nitric acid, 2 ml of ferric ammonium sulfate solution, and titrate with the ammonium thiocyanate solution to appearance of reddish brown color. Next, Fajan's method. Fajan's method is named after Casimir Fajan uses dichlorofluorescence as an indicator, and the end point is observed when the green color of suspension turns pink. In 1923 to 24, Fajan introduced this method, Fajan's method. Absorption of indicator used. The action of these indicators are based on the simple fact the end point indicators get absorbed by precipitate, and during the process of absorption, a change in color of the indicator will take place as a result of substance different color. Theory. Casimir's Fajans introduced the useful indicator for the precipitation titration by studying the nature of the absorption. At an equivalence point, these indicators get absorbed and the precipitate, resulting in a color change. These indicators are either basic dyes or acidic dyes. Acidic dyes, example, fluorescein and eosin. This method is used to the property of colloidal precipitate to absorb its own ions present in excess amount. When sodium chloride is titrated with silver nitrate, excess of chloride ion get absorbed on silver chloride precipitate, forming uniform layers. Thus, the primary absorbed layer of chloride ions hold the secondary absorbed layer of sodium ions. After the equivalence point, the silver chloride absorbs excess of silver ions present as the primary absorbed layer of nitrate ions in secondary absorbed layer. Fluorescein and its derivatives are absorbed to the surface of colloidal silver chloride. After all chloride is used, the first drop of silver is react with the fluorescent, forming the reddish color. Among these methods, Oldhart's method is widely used because we can detect the end point of precipitation titration very well. Limitations. A fewer number of ions such as halide ions, chlorine, bromine, iodine can be titrated by precipitation method. Co-precipitation may be occurred. It is very difficult to detect the end point. Determination of end point. Formation of colored precipitate. In Morse method, a small quantity of end point of the chromate ions combines with the silver ion to form sparingly soluble silver chromate. Silver chromate is sparingly soluble in water but not more soluble in silver chloride. The red color does not appear until the chlorides are precipitated. In determination of neutral halide, 0.5 ml of 0.5 percentage weight by volume of potassium dichromate is used. In acidic solution, potassium dichromate cannot be used as an indicator because of the solubility of potassium chromate in acid. Acid solution neutralized with chloride-free calcium carbonate and sodium bicarbonate. Alkali is acidified with acetic acid and slight excess of calcium carbonate. The solubility of silver chromate is increased with the temperature of the titration must be performed at room temperature. Formation of soluble colored complex. It is explained by Oldhart's method of titration of silver in the presence of free nitric acid with the standard potassium or ammonium thiocyanate solution. The indicator is ferric nitrate or ferric ammonium sulfate. Addition of thiocyanate produces a first precipitate of the silver thiocyanate. When this reaction is complete, the slight excess of sodium thiocyanate produces reddish brown color due to the formation of complex. It is applied to determine the chlorides, bromides, and iodine acid in the solution. When excess of silver has reacted, thiocyanate may react with the silver chloride since silver thiocyanate is less soluble. It takes place before the reaction occurs with the iron 3 ions with cause titration error. It is necessary to prevent reaction between the sodium thiocyanate and silver chloride. Silver chloride is filtered off before titrating since the stage of precipitate will be contaminated with the absorbed silver ions. The suspension should be boiled for a few minutes to coagulate the silver and then remove the most absorbed silver ions from its surfaces. After the addition of silver nitrate, potassium nitrate is added as a coagulant. The suspension boiled for about 3 minutes, cooled then and titrated immediately. Reabsorption of silver ions occurs on cooling and reabsorption large, preventing the present area. An invisible liquid is added to coat the silver chloride particles, thereby protect them from irritation and with the thiocyanate. Application standardization of unknown NaCl is used. Standardization of silver nitrate and determination of complexes. Fluorescent. Important dye with phthalate group condensing phthalic anhydride and resonance. 0.3 solution sodium sulfur-fluorescein is water by alcohol and Wolf recommended 1 to 2 drops of indicator for 10 ml of 0.1 halide. It is rapidly decomposed by light. It can be used for chloride, bromide, iodine, and thiocyanate. It is a weak acid solution condensing phthalic anhydride monochloride resonance. 0.1% of solution, 70% alcohol, and 0.1 solution as indicator. Thank you.